So welcome to our first lecture on Chapter 14, dealing with the behavior of solids and liquids. So we can consider a simple gas law problem. What is the volume occupied by 1 mole of steam in a piston at 105 degrees Celsius if the pressure in the piston is 95.2 kilopascals? Well, we're given an amount of gas, steam is a gas, a temperature, and a pressure. That means we have all the requirements to calculate. PV equals nRT, divide both sides by P. V is equal to nRT divided by P. 1 mole of gas, the pressure is 95.2 kilopascals, the temperature is 378 Kelvin, because you always have to use absolute temperature, and that means we have to use the 8.314 for our R, since it includes kilopascals. Do the calculation, 33.01147, etc. Moles cancel moles, kilopascals cancel kilopascals, Kelvin cancels Kelvin, and so the volume should be 33.0 liters. If we push the piston down and make the new volume 20 liters, what's the new pressure inside the piston going to be? Well, you could actually solve this two ways. You could try and solve it as a Boyle's law problem, or you could simply go ahead and use PV equals nRT. P equals nRT divided by V. Still have 1 mole. Volume's 20 liters now, temperature 378 Kelvin. Again, we're going to have to use the 8.314 R. Moles cancel moles, Kelvin cancels Kelvin, liters cancel liters, and we get a pressure of, well, it's 104 kilopascals. 104 kilopascals. That's not what the calculation says. The calculation says it should be 157 kilopascals. But unfortunately, the right answer is 104 kilopascals, not 157 kilopascals. So what's going on? What's going on is reality. PV equals nRT is what is known as the ideal gas law. Well, what makes something an ideal gas? Well, an ideal gas cannot be condensed out of the gas phase under any conditions. Its particles have no attractive forces for each other and therefore have no reason to condense out of the gas phase. The problem is, no real gases qualify as ideal gases. Any real gas, under some conditions, can be condensed out of the gas phase. And so there are no real ideal gases. Actual gases don't fit as ideal gases. Since any real gas can be condensed out of the gas phase, that means the particles must have attractive forces between each other. And we in fact talk about the intermolecular forces. The intermolecular forces are the attractive forces which condense real gases out of the gas phase. And the first of the attractive forces are London forces. Consider a sodium atom in the gas phase. The sodium atom would consist of its small, tight, positively charged nucleus, 10 electrons packed in a neon configuration, and finally its last valence electron. And the last valence electron, of course, is moving all around, and over any length of time, the atom ends up looking spherical. Suppose we bring up a second sodium atom going to collide with the first one in the gas phase. What's going to happen? Well, as those two atoms come together, those outermost valence electrons are going to start seeing each other, and they don't like each other. But that's not a problem for the electrons. As far as the electrons are concerned, these two atoms are coming together in slow motion. They're moving very slowly. The electrons are very fast. So the first electron on the first sodium can simply avoid the second electron on the other atom by just spending more time on the left side than on the right side of the atom. But this means the left side of the atom is becoming somewhat electron-rich, whereas the right side is becoming electron-deficient. In other words, we're generating a small dipole on the first atom. If we switch to the second atom, its outermost electron, is going to see this small positive charge on that side of the first atom, and so be attracted to it, and spend more time on that side of the atom than on the other side. And so we see the second atom starts having a dipole appear. Well, the more time the electron spends on the left side of the second atom, the less time the electron on the first atom is going to want to spend near it, and it's going to spend even more time on the left side of the atom. So its dipole is going to be reinforced. And of course, making that dipole reinforced will reinforce the dipole on the second atom. And so we have in fact created a dipole-dipole attraction between the two atoms. We talk about an instantaneous dipole. And it's coming about because the electrons are simply getting ready to collide with each other. And so we have the first of our intermolecular forces, the London forces, sometimes also referred to as the instantaneous dipole, because that's what it is. The asymmetric motion of the electrons as the two atoms come together to collide create minuscule dipoles, and those dipoles attract. Now, obviously, this is not going to be particularly strong force. It's very short range. It only comes into play when the atoms happen to be very close together. After those two atoms collide and bounce off and move away, those dipoles will completely disappear. So this is a very weak force and very short-ranged. On the other hand, all you need to have this happen is a positively charged nucleus and at least one electron moving around it. And who qualifies as having a positively charged nucleus and at least one electron? And the answer, of course, is everything. That's what all the atoms are. So any real gas automatically has to have at least the London forces, because anything that's made out of atoms will have the London forces. And so the London forces are ubiquitous, but they much stronger than the London forces are a dipole-dipole attraction. In a molecule like iodine chlorine, the iodine puts in one, the chlorine puts in one, we get a covalent bond, everybody ends up with their octet around them, and everybody's happy. Well, no, everybody's not happy. The chlorine is much more electronegative than the iodine, and so it pulls those electrons conspicuously to its end of the bond. And so the chloride ends up somewhat electron-rich, and the iodine ends up somewhat electron-deficient. And so in this case, we have a dipole, and that's a permanent dipole. The chlorine end is always somewhat negative, the iodide end is always somewhat positive. And this has the effect of, like we said, of turning the molecule into a small magnet. And the important thing is, magnets attract other magnets. They attract each other strongly. That dipole is always there. Unlike the London forces, which are just temporary and show up and disappear, that dipole is always there. It is always actively trying to pull other dipoles in. And so we see the dipole-dipole attraction is a much more effective way of condensing gases out of the gas phase. Our third intermolecular force is a special case. And special cases involve, guess who? Hydrogen. And so our third intermolecular force is hydrogen bonding. Like we said, in a molecule like iodine chloride, the iodine is in fact ending up somewhat positive. It's somewhat electron deficient, and so it's the positive end of the dipole. But it's not an ion, and it's not because the iodine is deficient in electrons. It still has a lot of electrons around it. It's only sharing 2 with the chloride. It still has 52 electrons all to itself. So there are plenty of electrons around the iodine, even though it's the positive end of the dipole. It's a different case for something like hydrogen fluoride. Again, the fluorine, more electronegative than the hydrogen is, pulls the electrons to itself, which leaves the hydrogen with what? Well, basically, it leaves it with nothing. All its electrons get pulled to the fluorine side. So it's not just that the hydrogen is somewhat electron deficient, it is almost a positive charge over there. And positive charges like negative charge. And so if we consider another hydrogen fluoride, the fluoride is the very negative end of the dipole, and it's got 3 lone pairs of electrons around it, which it's not using for anything in particular. They're just there. And so we see this desperate hydrogen, almost cation on the hydrogen end of the HF, latch on to those lone pairs of the other fluorines as they go by, and we get what is known as hydrogen bonding. And this attraction is really strong. It is almost an ionic type attraction. Anything that has hydrogen bonding in it will be real easy to get out of the gas phase. Well, if all real gases have intermolecular forces, then why don't they all condense at the same time? And it's because they have different amounts and different variations on the different forces. They all have London forces, but the London forces are aided by certain things. They're aided by heavier particles. Heavier particles move slower in the gas phase, and therefore if we compare argon and neon, which are both atoms in the gas phase, the argon has an atomic weight of 39, the neon 20. And so the argon atoms would be moving much slower, and therefore it would be easier for the London forces to condense the argon compared to the neon. London forces are also aided by large particles, that is, things that have more atoms in them. They tend to be larger. And so in a comparison between methane, which has a molecular weight of 16, and neon, which has a weight of 20, the neon's moving a little bit slower, but it's only a single atom. Whereas the methane is a molecule. It's got 5 atoms in size. It'd be 2 or 3 times as large as the neon would. And so even though they are very close in weight, it will be much easier to condense the methane simply because it is a much bigger molecule. And so we see for London forces, it's easy to condense big, heavy molecules out of the gas phase. It's going to be really hard to condense small, light molecules out of the gas phase. The obvious requirement to have a dipole-dipole attraction is you've got to have dipoles. You know, that's why we went through all that structural information for VSEPR. It's so you could tell if the molecules were polar or not, that is, if they'd have dipoles. And we said our requirement for dipoles is 1, you have to have polar bonds. Somebody has to be a lot more electronegative than whoever they're bonded to. But polar bonds by themselves are not sufficient. You also have to have asymmetric shape. And if you have both polar bonds and asymmetric shape, you get polar molecules, and they have a dipole-dipole attraction. So if we were going to compare iodine chloride with bromine, as far as London forces go, they both weigh about 160, and they're both 2 atoms in size. They're about the same size, and they're almost the same weight, but the big difference is the iodine chloride has a permanent dipole. The bromine has only the London forces, and so it'll be much easier to condense the iodide chloride out of the gas phase compared to the bromine. Which brings us finally to hydrogen bonding, which we said was a special case. The requirement for hydrogen bonding is you got to have a polar bonded hydrogen. If hydrogen is close in electronegativity to whatever it's bonded to, you don't have a polar bond. It's only when hydrogen is bonded to something very electronegative that all its electrons get pulled away from it. But just having a polar bonded hydrogen is not enough. It's got to have something it can latch onto. It's got to have small lone pairs somewhere else in the molecule. Those 2 requirements basically say you have to have a hydrogen bonded to oxygen, fluorine, or nitrogen somewhere in your molecule if you're going to get hydrogen bonding. If hydrogen is bonded to anything else, it's not going to be hydrogen bonding, and if there's no oxygen, fluorine, or nitrogen available, it won't have anything it can latch onto. So a requirement for hydrogen bonding is you have to have oxygen, fluorine, nitrogen in your molecule, and the hydrogen has to be bonded to it. And that brings us to the end of our discussion for today of intermolecular forces. See you next time.